All right, let's continue with the rest of the problems in 1.4. So we were on part D, which looks at element orders. In H over the integers mod 2, right? So let's take a look back at what it said specifically. Okay, let me just move this. All right. So find the order of each element of the finite group. Integers mod 2. So the finite group H over the integers mod 2, sorry. Right. Okay. Let's see. Give me a moment. Gotta get this thing set up. Okay. So let's write x with parameters a, b, c, which is equal to the matrix 1, a, b, 0, 1, c, 0, 0, 1, with a, b, c in the set 0, 1. So a standard power formula. Dang it. Proved by induction is x of a, b, c to the n is equal to the matrix 1, na, nb plus combination of n2, ac, 0, 1, nc, 0, 0, 1. This is over the integers mod 2. Two here is equal to 0 in this case, and well, for mod 2 and 2 in combinations with 2, so is equal to 1. So, oh no, so I run out of space, that's why. So, x with a, b, c, x of a, b, c squared is there and equal to 1, 0, ac, 0, 1, 0, 0, 0, 1. All right? Now, there's more to this. So, let me see. Okay. Hence, every element has order dividing 4. And let's do a quick check of this. Okay. what do we have there? Well, for order 1, we have the identity 1, 0, 0, 0, 1, 0, 0, 0, 1, right? Order 2, we have 1, 0, 1, 0, 1, 0, 0, 0, 1. We also have 1, 1, 0, 0, 1, 0, 0, 0, 1, and 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 1, 0, 0, 0, 1, and finally 1, 0, 1, 0, 1, 1, 0, 0, 1. Order 4, what do we have for that? Well, we've got 1, 1, 0, 0, 1, 1, 0, 0, 1, and finally 1, 1, 1, 0, 1, 1, 0, 0, 1. Okay. Just a bit of a quick check there. So indeed, x of 1b1 squared is equal to 1, 0, 1, 0, 1, 0, 0, 0, 1, which is not the identity. Squaring again gives the identity. Squaring again gives I. And what were we asked for problem D, right? So for problem D, we were asked to find the order of each element of the finite group. H over the integers mod 2, and that we did. Now onward to E. Might be able to finish this a bit early. So for part E, we're asked to prove that every non-identity element of H over the reals has infinite order. Quite a task, right? So, for E, let's see, infinite order in H over the reals via an inductive power formula. So our claim for any field F and any x of A, B, C is equal to 1, A, B, 0, 1, C, 0, 0, 1 is contained within H over F. So for any of those and for any field and any such matrix C, one has for every integer, for every n for every integer n greater than or equal to 1, x of A, B, C to the n is equal to 1 times NA, 1, then NA, then NB plus combination N and 2 times AC, then 0, then 1, then NC, then 0, then 0, then 1. Right? That's what we want to show. So, well, that's part of what we want to show. So let's go ahead and prove that via induction. All right, so using the multiplication rule, from part A, whoops, I'm skipping a step. Okay, so we're gonna do this by induction. So for n is equal to 1, this is our base case, right? So the formula is immediate. So assume it holds for some n greater than or equal to 1. Well, what we then have is that, okay, x of n is equal to 1 na nb plus the combination n2 of n and 2 times ac 0, 1, nc 0, 0, 1, right? So now using the multiplication rule from part A, what do we get there? Well, we get that matrix 1, A sub 1, B sub 1, 0, 1, C sub 1, 0, 0, 1 times matrices, times matrix 1, A sub 2, B sub 2, 0, 1, C sub 2, 0, 0, 1. What does that get you? That gets you matrix C1, A1 plus A2, and then for that third entry there, B sub 1 plus A sub 1 times C sub 2 plus B sub 2. Okay, that's what we get for this position over here. Just ran out of space. Then we get 0, 1, C1 plus C2. We get 0, 0, 1. Right? Okay. Now, let's take A sub 1, B sub 1, B sub 1, C sub 1, what do we get? That equals NA, NB plus, okay, A sub 1 comma, B sub 1 comma, C sub 1 comma. So that's equal to NA comma, NB plus combination of N and 2 times AC comma, NC. Okay, how about for A sub 2, comma, B sub 2, comma, C sub 2? Well, we get A comma, B comma, C. What does that mean for x to the n plus 1? Well, that's equal to xn times x, which is equal to x to the n times x, which is equal to 1 times n plus 1 times a times this ridiculously long thing, which is just, let me just get that, which is open parentheses nb plus combination of n and 2 times ac plus open parentheses na close parentheses times c plus b, okay? And 0, 1, open parentheses n plus 1 times, close parentheses times c, 0, 0, 1, right? So, and the first row, third column entry simplifies using open parentheses, using the combination of n plus 1 and 2, n over 2, which is equal to, combination of n and 2 plus n. So that would get you, just gotta erase this really fast. So that gets you, open parentheses, NB plus combination of N and 2 times AC, close parentheses, plus N, AC plus B is equal to, open parentheses, N plus 1, close parentheses, times B plus, open parentheses, combination between N and 2 plus N, close parentheses, times AC, which gets you, open parentheses, N plus 1, close parentheses, times B plus combination between N plus 1 and 2 times AC. So, the formula holds for N plus 1, which means our induction step is completed. Well, yes. And so let's get a better look at this in terms of what it means for what we're solving more directly. So let's let x of a, b, c be within h over r with x not equal to the identity. Now, by the formula, which we showed was true, x of a, b, c to the n is equal to the major C1, the identity 1, 1, NA, and then NB plus N times open parentheses N minus 1 over 2 times AC, then 0, then 1, NA, this is supposed to be NA, goodness gracious. Then NC, then 0, then 0, then 1. So, if A is not equal to 0, then the first row, second column entry is NA not equal to 0 for all n greater than or equal to 1. Now, if C is not equal to 0, then the second row, third column entry is NC not equal to 0 for all n greater than or equal to 1. This continues on. Let me get to that. Don't like finite board space. It would be nice if I could just kind of scroll. Maybe I'll get like an iPad or something and do that. But then again, I lose kind of the feel for it, but I don't know. So if A is equal to C, which is equal to 0, but B does not equal 0, then the first row, third column entry is NB is not equal to 0 for all n greater than or equal to 1. So no non-identity element can return the identity element, return to the identity element in finitely many steps. Okay. So every non-identity element of H over the reals has infinite order. Okay. QED for the exercises in 1.4 matrix groups, and we are good to go there.